Hey everyone, and welcome back to The Explainer. I am absolutely thrilled to guide you through today's topic, mostly because it is the hidden machinery behind basically every massive human achievement. Have you ever wondered how a towering skyscraper, a complex software launch, or a new manufacturing plant actually gets off the ground and finishes with flawless precision? Well, today, we're going on a journey through the construction of a massive project. We're going to start way up high, looking at the broad project launch, and then we'll zoom all the way down to the micro-level statistical checks that ensure perfect quality. Here's our roadmap for today. We'll start with the project lifecycle, then look at time, cost, and crashing. Next, we'll map things out with PERT and CPM networks, move into Six Sigma and Deming, and finally, wrap up with statistical control charts. Let's get right into it. All right, section 1, the project lifecycle, the blueprint of operations. So, our source material defines the project lifecycle quite simply as the specific time necessary to complete an entire project. But here's the real kicker. That project schedule? It is developed right out of the gate during the initial planning phase. It's literally like laying the foundation of a massive skyscraper. Before a single drop of concrete is ever poured, every future step is plotted out. This planning phase sets the baseline for absolutely everything that follows. Moving on to Section 2, Time, Cost, and Crashing, the ultimate balancing act. Because let's be real here, no matter how perfect your initial planning phase is, reality happens. Deadlines loom, and suddenly you are forced to navigate the brutal constraints of time and cost. What's really interesting is the direct trade-off managers face. If time delays start to jeopardize the success of the project, you have to shift your resources. Consequently, as the schedule falls behind, costs naturally tend to increase just to get the project back on track. Basically, if we fall behind, we have to spend more to catch up. It is a universal law of operations. So how exactly do we spend that money to catch up? Enter the superhero tool of project management, project crashing. Crashing is a specific method used for shortening the overall project duration. You do this by taking one or more of your critical activities and reducing their time to less than normal. Essentially, you're hitting fast forward to complete the project with all possible haste. But as you might guess, that haste comes at a serious premium. To really understand the financial stakes of crashing, let's look at a concrete example from our source data. If a project requires a total crash cost of 27,568 rupees to shorten the schedule over an 8-week period, your crash cost per week is a staggering 3,446 rupees. Every single week you shave off burns through that capital. That is exactly why managers have to calculate precisely which activities are actually worth the cost of crashing. And to know exactly which activities to crash, we need to map out the master plan. This brings us to Section 3, PERT and CPM networks, mapping the master plan. The crucial point here is understanding the nature of your project so you can pick the right mapping tool. Is your project highly predictable, like a standard manufacturing assembly line? If so, you'd use CPM, the critical path method. CPM uses deterministic activities, it's activity-oriented, and it's absolutely ideal for linear works. On the other hand, if your project is highly uncertain, say a brand new research and development initiative, you'd use PERT. PERT stands for Program Evaluation and Review Technique. It's event-oriented and relies on probabilistic time estimates, mostly because you just aren't sure exactly how long things are going to take. But regardless of whether you use PERT or CPM, the ultimate goal of network analysis is always to reduce the overall project duration. Structurally, these networks are drawn using formats like activity on arrow or activity on node. To build the timeline, you follow specific rules, like determining the earliest start time by comparing an activity's end time to a previous one. But the really valuable part is calculating slack. Let's do the math. If a task has a late start allowance of 8 weeks, minus an early start of 2 weeks, you get 6 weeks of slack. Think of that as 6 weeks of precious breathing room in your schedule, where delays won't completely ruin the whole project. All right, Section 4, Six Sigma and Deming, engineering flawless quality. So we've mapped the timeline, crashed the schedule, and built the project. We're done, right? Not even close. We now have to ensure the output is perfect. This brilliantly illustrates the absolute bedrock of modern quality management, W.E. Deming's 4-step cycle. Deming championed this incredibly simple yet powerful iterative loop: plan, do, check, and act. It's a relentless cycle of setting a standard, testing it out, analyzing the results, and taking action to improve. And this philosophy of continuous improvement culminates in the ultimate quality benchmark, Six Sigma. I really want to hit you with the sheer scale of Six Sigma's ambition here. Processes operating at Six Sigma quality aim to produce long-term defect levels below 3.4 defects per million opportunities. Think about that for a second. For every 1 million chances to make a mistake, you are only allowed 3.4. That is mind-blowing precision. Of course, maintaining that precision involves the cost of quality. These initiatives are usually led by certified black belts and green belts. You're making investments in internal costs, things like inspection, scrap, and repair. Now, why spend so much internally? Because it stops massive external expenses from popping up later. By catching defects on the factory floor, better quality drastically decreases your long-term maintenance, warranty, and service costs. Section 5. Statistical Control Charts, the micro-level diagnostics. So, how do those black belts actually catch defects in real time? We zoom into the actual diagnostic tools used for statistical process control charts. To read one, you just need to understand its visual boundaries. Right in the middle is the center line, representing the average value of the quality characteristic when everything is perfectly in control. Above that is the upper control limit, the absolute highest value allowed before the process is out of control. And down at the bottom, we have the lower control limit, the minimum acceptable value. If your data points step over those lines, alarms should be ringing. There are different charts for different diagnostics, but two vital ones you really must distinguish between are the P chart and the C chart. The P chart uses the proportion of defective items in a sample. It's looking at ratios. The C chart, however, uses the exact count, or the actual number of defects per item. Choosing the right chart depends entirely on exactly how you need to measure your errors. Let's look at a concrete mathematical application of a P chart. Imagine you have an average daily inspection quantity of 50 items. Historically, your percentage of defective items is exactly 0.05. Using statistical process control formulas, your upper control limit locks in precisely at 0.14. So if a daily sample suddenly shows a defect proportion of 0.15, you have breached the limit, and management must intervene immediately to find the root cause. But I want to leave you with a fascinating, almost deceptive scenario. Imagine you're staring at a control chart. None of the data points have crossed the upper control limit. None have crossed the lower control limit. In fact, 18 out of 20 consecutive points plot securely between the center line and the upper control limit, while only 2 fall below the center line. It hasn't broken the boundaries, so what is the state of the process? The answer is, it's out of control. Why? Because statistical process control isn't just about hard limits. It's about spotting non-random variation. 18 out of 20 points hovering above average proves there is a fundamental, non-random shift in the system that needs fixing. It kind of makes you wonder, doesn't it? What subtle and visible trends are currently hiding inside your own data, quietly signaling a broken system? Keep analyzing, keep asking questions, and I'll catch you in the next explainer.